In this video, I'm just going to talk a little bit about the gradient. Sometimes people, when we're doing special relativity, they'll explicitly call this the four gradient or the four derivative. And that's because this object is actually going to behave like a four vector, but it's going to be a set of derivatives. And so this is usually written simply as sort of partial mu. So this is our four gradient. So it's going to have our four components, which shorthand, usually we'll write them this way. But really, this is our set of partial derivatives. So this is the partial derivative with respect to t, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. And that's it. And so we could take our four gradient of some scalar function. So here, this is just a function. It's not a four vector itself. So this thing is a four vector, which looks like d phi t dt, d phi dx, d phi dy, d phi dz. All right, or we could consider taking our gradient of some four vector itself, right? This is a scalar because this is like doing a dot product. So this is dx, oh, excuse me, t is first. dt at plus dt, sorry, dx ax plus dy ay plus dz az. All right, so that is our four gradient, and we can act it on other things. It's going to transform like a tensor if we want to transform between different coordinate systems, right? So here I wrote it explicitly. So this is we're imagining we're in some reference frame S with coordinates t, x, y, and z. And so this is what our gradient would look like there. If we transform into some S prime, and we want to now take a derivative with respect to t prime, x prime, y prime, and z prime, we can relate these things by doing Lorentz transformations, just like we do with other four vectors. So it's going to be really handy that this thing itself is going to behave like a four vector. All right, so that's some of the basics of the gradient in special relativity.